In the remaining time, I will talk about techniques for proving dynamic data structure lower bounds. So again, we'll have one running example of a dynamic data structure problem that we will apply probably two techniques on. It's basically the dynamic version of the polynomial evaluation problem we saw earlier. So dynamic polynomial evaluation. So the problem we're going to focus on, the example we're going to focus on is the following. So we want to maintain a polynomial of degree n minus 1, p of degree n minus 1 over fq again for q that is polynomial n, and supporting two types of operations. One is the queries, which is the same as before. So and supporting the queries. In each query, we'll get one element x from the field, and we must return p of x. Second, we'll handle the updates, which has a form that we are giving one of the coefficients and also one number from the field, and we set okay, maybe I should say this polynomial is p of x equal to an minus 1 x to the n minus 1 up to a1 x plus a0. And then we just set ai to this new number. Okay. And then in dynamic data structures, we care about how much time it takes to handle each update and how much time it takes to handle each query. And usually the point here is try to understand, or the question here is try to understand the trade-off between the query time and the update time. And the update time. And usually the space is not, I don't know, a parameter that will come into play. But in the data structure design, this is sometimes also important. And most of the lower bounds will not, I guess it will not depend on the space. It just describes for a given query time what is the smallest update time and so on. And one other parameter that is also important for dynamic data structure is the max of the two, just one lower bound, max of the query time and the update time. And then, so we will use TU to denote the update time and TQ to denote the query time, and want to prove a lower bound on the max of the two. Okay. So the problem setting clear? All right. So the first technique I'm going to talk about is called the Chronogram argument, actually by Michael Fredman and Michael Sachs. In 89. Okay. So what is this argument? So let's focus on the following type of operation sequence. So we'll do a bunch of updates. Let's say a sequence of n updates. So consider a sequence of operations as with the following form. So we'll first do a bunch of updates, in total n of them, and then we will do one query at the end. and one query. And the goal here is try to analyze if my update time is bounded by TU, then how much time I need to answer this final last query. All right. And for simplicity, for this problem, let's just assume that the ith update will update the ith coefficient. So this update will update 0's coefficient, and this updates the first coefficient, and so on. So this sequence of updates after the n updates will actually determine the polynomial. We can assume that the polynomial was 0 at the beginning, but it doesn't really matter for this update sequence, right? Okay, so now here is the argument. So we get n updates, and then we are going to divide this sequence of n updates into blocks of updates, which are called the epochs. So divide the sequence into epochs. So the size of the epochs will be geometrically decreasing. So we have this sequence of updates. The first epoch will be most of the updates in the sequence. And the second epoch will be something smaller, and the third one will be smaller, and so on. And in general, we name the last epoch the epoch 0 for some reason. And then this is epoch 1, such that the size of so that epoch I will have about, let's say, equal to beta to the I updates. So the length of the epochs are geometrically decreasing for some parameter beta that is that will be set to the update time times the word size to the some power. Okay. So we have got the sequence of n updates. We are going to divide the updates into epochs, just virtually, such that the ith epoch will have beta to the I updates, and the size of the epochs would geometrically decrease. Okay. Then we're going to look at the query algorithm at the end that answers this query. So first, of course, because all these updates will affect the final polynomial, so my query answer will definitely depend on each of these epochs. And let's see if we have an epoch I in the middle. So how does the query algorithm learn what has happened here? So we fix an epoch I here. Okay. So to learn information in epoch I, to learn information about the updates in epoch I, so the query algorithm can access different types of cells. So first, if a cell that has not been updated or has not been probed since the beginning of this epoch, then if there's such a cell, then probing those cells will not give you any information about what has happened in epoch R, right? Because those cells, the last time it was updated, you have not even seen the updates in epoch I yet. So for cells that are not probed since the beginning of epoch I, these are useless for you to learn information about epoch I. So not useful. Okay. Now let's also look at the cells. So there are some other cells that has been accessed after the end of epoch I. So recall that the next one is epoch I minus 1. There are some number for those cells. And those cells can be useful, right? Because as you update these, as you perform those updates, you may also probe some cells that has been updated here. Then maybe you can carry some information to those cells. So those cells can be useful. But because of the design of our epochs, we have geometrically decreasing sizes, and we have bounded update time. So this means that we cannot have too many of those cells. So for the cells that are probed after the end of the epoch I, so how many of them? There are only beta to the I minus 1 different updates after epoch I, and each one of them can update at most TU cells, and each cell can have W bits in it. So this is because we set beta to be TU times W times a polynomial. This is something much smaller than beta to the I bits. Right? So they can be useful, but they just contain too little information. Too few cells. So this means even if we read all of them, that's not enough information for us to know sufficient about what has happened in epoch I. So this means we have to rely on the rest of the cells, which are the cells that are probed after the beginning of epoch I, but not probed since the beginning of the next epoch. So cells that are probed after the beginning. Maybe I should say this. So equivalently, this is a set of cells that whose last time was probed was in epoch I. Probed in epoch I, but not later. And we have to rely on those. And then for simplicity for notation, we just denote this set by Ci. So denote by Ci this set of cells. Okay. So the main lemma that will derive the lower bound is the following, that we must, for a random query, we must probe at least one cell from Ci in order to learn some information about epoch I. So the main technical lemma is the following, that for a random update sequence and a random query, for this problem, we must probe at least one cell in Ci in expectation.
This is for most I, or?
For every I. For every I. Yeah. So because this argument just says for some I, we have those type of cells, and then this is actually true for every I. So suppose we can actually prove this lemma that a random query must probe something from this set, and because by definition set Ci is just a set of cells that are probed in epoch I but not later, so these are disjoint cells for different I's, right? So this would actually imply a lower bound that is proportional to the number of epochs here. So lemma implies that the query time is at least omega of the number of epochs, which is log base beta of n, which is log n over log of beta, which is tu times w. Right. So in particular, this means that when the update time tu is polylog n and w is also polylog n, is also log n, then the query time is at least log n. Log n over log n. And in particular, the max of the two must be at least log n over log n. Okay. So before I show you a proof of this lemma, any questions about any questions so far? All right. So this lemma is proved by doing an encoding argument. I guess there are probably other ways to do it, but I'm going to present the following argument. So consider the following setting where we have two players, one encoder and one decoder, such that the encoder knows a polynomial that can be uniquely described by a sequence of updates. So encoder knows a polynomial p, which is basically the update sequence. And then this encoder wants to send this polynomial to a decoder who doesn't know anything. Just encoding a decoding process, right? And assuming, for simplicity, let's assume they have public random bits, shared random bits, right? So if there's an encoding scheme such that this can happen, then this means the communication from the encoder to decoder must be at least this log of the size of our possible inputs, which is n log q. So any such scheme must have or n log q bits of communication. Okay, so the main idea is that suppose we have a data structure where this is not true. That means for most of the time and for most of the queries, the query doesn't probe any cell in CI. Then we are going to use that data structure as a way to derive a very efficient encoding scheme for this problem. And the basic idea is that if you don't probe anything from this set CI, that means you don't actually need to know these updates in order to answer the queries, basically. And then if you can answer too many queries this way, then that will actually allow you to reconstruct this epoch, and then that will give you a contradiction. So more formally, so how do we do here? So first, the encoder, so for the encoding process, for encoder, we'll first encode all the updates that are not in epoch I. Okay. Naively, and okay, and then encoder will also encode everything that are useful but not too many. So we encode all the cells that are touched after the ith epoch. So by just writing down the contents and the addresses. After epoch I. Okay. Now if we have a data structure that probes no cell in CI most of the time, then we can do the following to describe a set of queries that can actually be answered without probing these cells in CI. So what the encoder will do is, because encoder knows everything about the update sequence, And he knows whether a given query will probe something in CI or not. So what they do is to use public random bits as infinite sequence of samples of sets of queries. Use public okay, so view the sequence, the public random bits as a sequence of sets of beta to the I queries. And then the encoder will send the index of the first set that doesn't probe anything in CI. Then the encoder will encode the index of the first set in the sequence let's denote this set by Q sub G, Q good, such that all queries in this set probe no cell in CI. Okay. So in this encoding process, we'll first encode everything that are not in the epoch I, and then we'll also encode everything that all the cells that are probed after epoch I, and then we'll try to use the queries, use the property that the data structure doesn't probe anything in CI with high probability to actually reconstruct, to describe a set of queries that actually has this property, and then we will try to use those queries to reconstruct the data structure, to reconstruct the input. All right. So is the encoding process clear? So first, just to quickly see that we can actually, from that, decode the actual update sequence. So in order to do decoding, we can first decode naively the updates that are not in there. And then also decode those cells. That are probed after epoch I. Okay, so from these two parts, we already can reconstruct the content of a cell that are not in epoch I, that is not in CI, right? So from so the claim here is from 1 and 2. We can, for any cell that is not in CI, we can already reconstruct its content. Any cells C that is not in CI, we can already recover its content. So why? Because if a cell that is never probed since the beginning of epoch I, then that means knowing the updates before epoch I, knowing all these updates, we can by simulating the update algorithm, we can already know its content at this point. But if it's not changed after that, then the content at this point is the content after all the updates, right? So for cells that are not probed since CI, we can compute it from these updates. And for the other cells that are probed after this the ith epoch, we describe it explicitly, so we also have it. Right. So from 1 to 2, we know the contents of all the cells that are not in CI. And from 3, we have encoded a set of queries that do not probe any cell in CI. So just by simulating the query algorithm on all those queries, we can reconstruct the output of these queries. So we just reconstruct or compute the outputs or the answers to all queries in CI in QCode. Right. So now this is sufficient information to recover the updates in epoch I, because we have answered to beta to the I points, and then by doing interpolation, that's what you recover. So this recovers the polynomial. And finally, we need to see that what is the number of bits that is sent from the encoder to the decoder in this process. So the length of the encoding. So the first part, it's just naively n minus beta to the I updates and times log q bits per update, maybe plus of 1 for rounding if necessary. And then for the second step, as we just calculated here, it's something much smaller than beta to the I bits. And then for the third step, now we are going to use the fact that most of the queries can actually be computed without probing anything in CI. So that means for a random query, the probability that it is not probing anything in CI is 1 minus lambda of 1. Right? So the probability that a random query X does not probe cells in CI is 1 minus lambda of 1, assuming assuming for contribution that this is not the case. Then that means if we want to sample a set of beta to the i's queries, then the probability that this is a good sample. So for a fixed set of beta to the a random beta to the I, a random set of beta to the I queries that all do not probe things in CI is this number to the beta to the I. So 1 minus lambda of roughly 1 minus lambda of 1 to the beta to the I, which is exponential in lambda of beta to the I. So for every sample we see in the sequence with this probability, this is a set that we wanted to have. So in expectation, the encoding length of this step is basically the exponent, right? So with the probability, so the expected length of encoding is lambda of beta to the I. So roughly at exponential in beta to the I sample in this public random bits, we will see one such good set of queries. And then by writing down its index, it takes much less than beta to the I bits. And then by adding 3 parts together, the total length is much smaller than n times q. So any questions about this argument?
Yes, so why can you decode the polynomial? You have some of the coefficients, you have the evaluation at some point.
Yes. Okay. So why can we recover the polynomial. So we know so we have a sequence of coefficients that is not known that is updated here, and we know all the coefficients outside this range, and we also know so there are beta to the I different coefficients here, and we know further beta to the I evaluations. So we can just first subtract the contribution from the other components to derive the evaluation of this chunk, and then also divide this x to the something, and then we do the interpolation. Okay. So any other questions? So in the original paper, it was proved a log n over log n lower bound for a dynamic partial sum problem. And that was tied for that problem when the updates are 1 bit. And then, so one other way to view this argument is that it basically reduces the problem of proving dynamic lower bounds to proving static lower bounds, and then gain a factor of log n over log n. So basically in this argument, we never use the fact that these individual updates. We just view each epoch as one batch updates, and then say that for those batch of updates, we update at most tu times the length of epoch many cells. And then we can update arbitrary sets of cells here and arbitrary set of cells here and so on. So in some sense, we can view this as a sequence of inputs to maybe log n over log n independent static problems, and each time we can update a set of cells that correspond to the space that we are going to use. So in some sense, in this argument, we can view it as a reduction from a static problem. Where the space of the static problem corresponds to the length of the updates, or length of the epoch, the number of the length of the epoch times the update time. And the query time, or the time, corresponds to the number of probes into CI. So I just want to mention that for a class of data structure problems which are called decomposable problems, this is basically tight. You can have a reduction from the other direction. If you have a solution to a static problem, then you can make a dynamic data structure from that by doing basically something like this. But I'm not going into detail for those problems. So the next, I guess the last technique I'm going to talk about basically is, I guess, uses this view, because we have seen a bunch of static data structure lower bounds already. So here, the only thing we are getting from the static problem is that it has to probe something from this static problem. So in other words, the query time must be at least constant. So if we plug in a stronger static lower bound, then maybe we can hope to get a stronger data structure lower bound for the dynamic problem. And that's basically what I'm going to talk about next. OK, I'll keep this one, and maybe first move this. So it's basically chronogram plus cell sampling, actually by Casper in 2012. Okay. So now the key claim that we want, or the key lemma that we wanted to prove is not just it probes one cell from CI, but it probes, say, log n over log n cells from CI. Okay, so the key lemma that we want to prove is that for this definition of CI, we must probe and log n over log n cells from CI in expectation. So why log n over log n? So if you remember the the cell sampling argument and the lower bound we got, it was basically log Q divided by log S over n, right? And in this case, if we view the space as the length of the epoch times TU, and the time as the number of probes to CI, then this epoch length times TU, and TU is something that is polylog in n, and this basically says that the denominator here is log n. So, and Q is a polynomial, so it's log n over log n cells. And suppose we do have such a lower bound on the number of cells, number of probes into CI, then this would actually imply a log n squared lower bound, or log n squared over polylog log n lower bound. Implies that the query time is at least, so log n, basically log n over log n squared for update time that is at most log n, polylog n. Right. So, okay. Okay, now how do we prove this this stronger lemma?
The word size here is
Sorry.
the word size.
Oh, yeah. I guess the word size is still O of log n. Yeah. I guess the concrete lower bound should be some. The more specific lower bound should be something like log n over log W times TU squared in general. All right. So just a quick recap of the cell sampling. We sample a subset of cells with some probability and then say that there are still many queries that can be answered if the query time is low. And then just by from the answers to those queries, we can probably reconstruct the polynomial if the number is greater than n. And then if the set of cells that we sampled is much smaller than n, then this is a contradiction. Okay. So we're trying to do the same thing here. Okay. So we're still going to do such an encoding argument. So first we'll encode all doublets that are not in epoch I. Then we also encode all the cells that are not probing after probed after epoch I. Now, for the next step, we are first going to do cell sampling. We're going to sample a set of cells in CI, and then we try to see what is the set of queries that can be answered by by only accessing the cells that are sampled and the cells that are not in CI. So basically what it means that we sample a set of cells and see what is the set of queries that do not access anything that is in CI minus the sampled set. Right? Okay. So yeah, let me just write below it. Okay, we're going to use this later, but let me first erase it. So for a random set of p fraction of CI, So if there's a data structure that violates this bound, then that means the probability that a query X probes no cell in Ci minus C, let's call this set C, is going to be at least roughly p to the little of log n over log n. Actually, maybe let me just write tu times w. Sorry. Right. And then still by setting p to be 1 over polynomial in that. So this is roughly to be 1 over polylog, 1 over tu times w to some power. This probability is at least 1 over n to the little of 1. So in total, we have polynomial in n many queries, and there's at least 1 over n to the little of 1 fraction of them can be answered by only looking at this set of cells and all the other information. So this in particular implies that there exists a set of C such that by doing basically the same argument as in cell sampling, such that at least Q times this P to the T, which is Q times n to the little n 1 over n to the little of 1 queries can be answered by only probing, by not probing cells in Ci minus C, right? So we sample a set of cells, p fraction set of cells, and then with some probability, if the query time is low, a cell can be answered by not looking at the unsampled cells. Then by linearity of expectation for a random set, the expected number of queries that can still be answered by not looking at the other cells is Q times this probability as before.
So what is it? I just can't read the Q times.
Oh.
How many queries?
Q times 1 over this. Q times this probability, 1 over a little of n to the little of 1. Yeah. So then there exists, in particular, there exists a sample that is as good as the expectation. So that means this set, by describing this set, there are at least Q times 1 over n to the little of 1 queries that can still be answered. So the next part of the encoding would just be encode this set. So both addresses and contents. Okay. So now we also need to describe what is the set of beta to the I queries that can be answered without looking at those cells as before, right? So before, most of the queries can be answered without probing anything in CI. So this calculation shows that the probability that a set of queries can be answered without looking at CI is something like this. So here the probability is much lower, but we can still get a contradiction from that. So the last step of the encoding is to view, as before, view this public random bits as an infinite sequence of samples of size beta to the I. Sequence of sets of beta to the I queries. And then we just encode the index of the first set as before. That does not probe anything in this set of cells. Okay. So the entire encoding, we first encode all the updates that are not in epoch I, and then we encode all the cells that are probed after epoch I. Then we do the cell sampling argument to show that there exists a set of cells, C, that is not too many, and at the same time there are a lot of queries that can still be answered by not probing anything in outside the sampled set. Then in the last step, we use public randomness to identify one specific set that has this property. So for the decoding procedure, I guess it's basically the same as before. We just decode every updates and decode the cells. And then from here, we also have seen the set C, and then we also decode the set of queries, and then all the cells that are not in this set, we all know its content, and then by just computing the outputs to these queries, we recover the same information as before. Right? So the only question here is, what is the length of this encoding? So the first two parts are the same, and we send less than beta to the I bits in the second step, and then for the third step, what do we write? We send a set of cells, C, right? And the length of the set is basically P fraction of Ci. And then we need W bits to describe the contents and the addresses. And here, because P we set to something like 1 over polylog n, much smaller than W, so this is, and much smaller than 1 over the update time. So this is much smaller than the number of updates in this epoch, right? Because we set P to be something sufficiently small. And we cannot probe more than TU cells per update. OK, so this is also cheap. Now, what is the number of bits we use to encode one such set? Basically, it's the same calculation. We first calculate what is the probability that a random query doesn't probe anything in this unsampled part of Ci. So this by the property of this cell sampling is 1 over n to the little of 1, right? And then now if we have a random set of beta to the I queries, the probability becomes 1 over n to the little of 1 to the beta to the I. And this is basically exponential in minus little of beta to the I times log n, or log q. That's the same. So the expected length of encoding of this part becomes beta to the I times log n. And if we sum up all the parts, we still get something that is smaller than the input size. So any questions?
Yeah, so in step 3, you sort of pulled out of the air, although, I mean, we kind of know why, the various parameters, the log, the exponent of p. And so if you let those be free, so how do we see that this is the best, that's the best result?
Good question. So here p is one parameter. I guess p is probably the only.
Well, the exponent. Let's see.
The exponent is the is a query time t that we are trying to prove a lower bound. But that was initially also a parameter, true.
That's right.
Yes. So initially this was p to the t. Maybe I should use ti as the number of probes to epoch I. So this is actually this. And then this just also is p to the ti. And in order to get a contradiction, we want sufficiently many queries to be answerable by not probing the unsampled cells. So that means we want this number to be greater than n in particular. So that because q is something polynomial in n, so this also at most can be a polynomial. So this gives a constraint on p and ti. For fixed ti, what is the smallest p you can have? And on the other hand, in order to encode C, we need to use that many bits. So this, in order to get a contradiction, this part of the encoding must also be smaller than the length of the epoch. So p has to be. So this adds another constraint that p has to be at least. At most 1 over the number of the update time and the word size, right? Because each cell in CI is something updated during epoch I. So this is at most the update time times the epoch size, which is beta to the I, right? And then we want this number to be much smaller than the information that is contained in those updates. So basically, we want something like this. Maybe we don't need a W, but up to polylog factors, this is the constraint we have. So yeah, I guess by combining these two constraints, the best TI we can have is something like log n over log. Okay. Yeah, that's a good question. Yeah, any other questions about this argument? Okay. Yeah, let me just briefly mention that in this argument, one important fact here is that we used little of beta to the I times log n bits to encode this set of beta to the I queries, right? And then from each query, we can recover basically log q bits of information about the data, right? So it's important that it takes fewer bits to describe a query than what it recovers from the query answer. Otherwise, we can never get a contradiction no matter how efficient the other parts are, right? So this in particular means that for problems where the query output length is very small, this approach basically doesn't apply. And in particular, this doesn't apply if the query output has 1 bit. So, so this approach does not apply, not applicable when output size is 1 bit. Or something much smaller than log n bits. And then a few years ago, Omri and Casper and myself has a similar but different but more complicated argument that can actually prove a lower bound for this case, but also proves a weaker lower bound. That is log n to the 1.5 on the max of the update and query time. So we got a log n to the 1.5 lower bound for in this setting, but on the max of update time and query time.
Can you repeat why it's not applicable?
Yeah. So from a technical point of view, if we look at this this argument, there was this fourth step where we want to describe or encode a set of beta to the I queries. And then in the decoding, we are going to use the output or the answer to those queries to recover some information about the part that we're not encoding. So in this argument, the length of this encoding is basically beta to the I times log n, a little of that for describing the queries, or on average, little of log n bits per query. So this means if the query output is much smaller than that, that means we cannot gain more information than that is needed to describe those queries from encoding that. Then this argument will not work in this case.
So what was the problem again? I do remember the paper, but I don't. Can you? What's the Boolean problem that?
Oh, the Boolean problem.
Go around?
Yeah. So I guess we proved that low bound for a few problems, but there was one that is 2D range counting, but range parity maybe. So that's the problem where we can insert. We're going to maintain a set of points on the plane, and then we can insert a point, or we can make a range query. Basically, we're giving a rectangle and ask what is the parity of number of points in there. Okay, and for these problems with 1-bit output, this is still the best lower bound we know. So an open question here is, can we match the lower bound for multiple output lower bounds and prove a log n square lower bound for this for any of these explicit problems? Sorry.
Is it type for this particular
No,
problem?
no.
For our approach, I guess.
Oh yeah, for our approach, we cannot hope to get a better thing, but get a better lower bound, but the upper bound is also still log n squared. So it's not tight.
I see.
In connection with the other problem, the running example, we also prove it for just outputting 1 bit of the
Yes.
like at least a bit or something.
Yes, so for this polynomial evaluation problem, we also prove a version where we just want to output the last bit of the value px. Yeah. Okay.
So Huacheng,
Yeah.
here, if you wanted to output the XOR of this point, would that be, like basically, is there any hope of proving some XOR lemma and then make this thing become log s square and lower bound? Because outputting 1 bit of the answer log n is not too hard, I imagine, to prove. And now you are saying that if you wanted to output the last bit, you can prove it with log to the 1.5. But last bit is usually harder than if you do, I don't know, either the majority of the bit of the answer or XOR of that.
Yeah. So, good question. At least the technique doesn't apply for 1-bit output. So, I guess.
But I'm
Yeah.
just trying to understand the question. So when you look at the last bit, I mean, for this particular polynomial evaluation problem, the last bit is not necessarily easy to get, right?
No,
Because-
definitely not. But
What?
last bit might be easier than getting something which is combination of other bits.
So I guess
Well,
maybe the
except that
encoding can be arbitrary.
What?
Yeah, I guess maybe that's what the
Right.
yeah, the encoding can be arbitrary. So the last bit can actually be viewed as any bit.
But it's still 1 bit, it's not a combination
Depends
of
on
the
one of
bits.
these. The first point is that maybe if you depend on all bits, the function is even harder.
I mean, you're already saying if I want to output all the bits, it's hard.
Yes.
You know?
We're doing it for range parity, right? For range parity, we're outputting the sum on 2, like the.
Yeah.
Right.
So I think he's
Right.
asking why parity and not some other function of the number.
Separate proposed XOR, which is parity.
So, So for the separity, for the polynomial evaluation, it's basically, so you're suggesting that we write down the bits of the output p of x and then output the parity, for example.
Yes.
But this is, you can view it as in a different encoding. This is actually the last bit of the encoding. Maybe the last bit is the parity. The second last bit is maybe the parity of the last some amount of bits and so on. So any last bit is basically any bit.
Good.
Do you have a nice explanation for this method, same way you did the previous ones, either in terms of the rectangle or reduction to some rectangular something or other?
You mean like which of?
This chronogram plus
Yeah.
whatever you call it, rectangle.
Yeah, chronogram plus self-sampling. Yeah. So there are other ways to do a similar arguments, which is chronogram plus some communication problem. I guess Omri and I, and also myself, has some other work that does something like this, where the second part is not self-sampling, but some communication game. But because it's I guess the dynamic problem setting is probably different from static. So the communication models we are using, we have to use in this reduction is not the standard models. And then there are some ways that we can prove a similar lower bound, but just the communication problem is not, communication model is not as straightforward as the static case. I'm not sure if this answers the question.
I'm going to take it as a no, but maybe I just didn't understand.
So there is some connection to a chronogram plus communication, just not the standard ones where we have two players and standard communication.
Okay.
Yeah. But there are other models of communication we can do something.
What are the best lower bounds for static problems with binary output?
That I think is log n. Log n over log n.
And what problem is that?
I guess the static range parity problem probably has this lower bound, I guess. So you don't have updates, and then you just have queries and ask the parity, if I remember correctly.
Yes.
In the static world, the cell sampling Alice doesn't need to send the set of doesn't need to specify the set of sampled cells.
Yeah. So basically, this step you don't need
shows
it.
up in the dynamic setup, so it's like right, because in the static world,
Yeah.
I mean, it's
Yeah, we just encode the set of sample the cells, and then by looking at the query, automatically knows if it only probes cells in there or also tries to probe something else. But in the dynamic case, we have to specify a set of queries that actually has this property, and that is the part that has something to do with the output size.
So why can't you use the public randomness to encode this set of cells? I mean, this holds for a random set.
Yeah. Oh, okay. There's one thing that it. You mean like to encode the set of cells, right?
So we know that a random set works, and then you pick a set.
Yes.
Suppose you don't pick a set. You just use your public randomness to specify a set.
Yes. I remember there is some convexity issue. For example, like with some very small probability, the sets for the set you will be able to answer all the queries. But for most of the sets, you answer maybe no query. Yes.
I think also maybe one thing is for the decision, like 1-bit outputs, it's this fourth step that the expensive one,
Yeah.
not so much. This one is anyways cheap. It's saying which queries
Yes.
you read in the cell. Like it's the fourth
Yes.
step that's the expensive one.
Yes. All right. If no question, we can probably go for lunch.
So maybe let me just say just to conclude the line of thought. So thanks a lot, Huacheng. So just to like mark where we finished. So the highest static lower bound we saw was this log n basically for linear space. The log squared over polylog is the highest dynamic lower bound. And basically what Huacheng showed us here is that if we ever hope to go beyond log squared n for dynamic, chronogram, despite its beauty and elegance, is probably not the way to go, because chronogram reduce it, like, if you prove a super log squared dynamic lower bound with chronogram, it would imply a super logarithmic static lower bound, right? Because chronogram is just a way to boost your favorite static lower bound by an extra logging factor. So if you want to prove a super log squared n dynamic lower bound, you have to use a completely different approach. And I guess Casper will tell us about this on Tuesday. So this is the multi-phase problem, and I guess also Pavel will talk about this today, right? So yeah, I guess I was hoping that we will already mention multi-phase, which is one of the main problems of the workshop. But yeah, so we'll see this on Wednesday, I guess. So
Yeah, I actually was planning to mention this, but I was running out of time.
All right, let's turn to what.
For
Yeah.
static, we have an excuse for why we cannot prove higher or lower bound. So we don't have it for a dynamic.
At
Right.
least, I think this is exactly right.
Okay.
For static lower bounds, proven super log would imply scary things that Sasha will show us on Thursday. And but for dynamic, at least the multi-phase problem does not seem to imply such dramatic stuff. Let's thank Huacheng again.